It's my pleasure to introduce our speaker today, one of our very own faculty members in the ECS. Many of you have probably had courses with Dr. Tabib-Azar. Massood received his MS and PhD degrees in electrical engineering from RPI, Rensselaer Polytechnic Institute in Troy, New York, 1984 and 1986. And then in 1987, he joined our faculty, and he's been here ever since, with a few visits here and there. 2 summers as a fellow at NASA, a sabbatical at Harvard, a sabbatical at Yale. He's now a professor in our department, and he also, you might not know this, has joint appointments in macromolecular and also in physics here at Case Western. He's interested in many different things. We know him for electronic devices, but he's also interested in nanometrology, NEMS, solid electrolytic devices, electrochemical interfaces to biological systems, and all kinds of sensors and actuators, and develops courses for all of those subjects. He's written 3 books, 2 book chapters, 120 journal publications, 200 conference manuscripts, so a very prolific publisher. He's a member of the New York Academy of Sciences, IEEE Electron Devices Society, and Sigma Chi. He's received the 1991 Lilly Fellowship and numerous other awards that you can read on the introduction to this talk. So I think with that, I'll let you begin.
Thanks, Steve. Thanks for your kind remarks. I hope that I can live up to that. I kind of tend to be more of an idea person than kind of detail person. So I hope that I won't bore some of you guys. I have been lucky with my collaborators that most of them are here, or some of them are here, to obtain funding from a variety of sources with Dr. Garbrick and with Dan Saab. We are working on a different proposal, and we have done lots of work with Dr. Ko in the past. My current funding is mostly from DARPA. You know, when you kind of talk about this type of figures, DARPA is probably the only agency that you can count on for that kind of funding, although there are center proposals and stuff that one can get from these other sources, but most of my funding are from DARPA. And today I'm going to talk about nanoelectronics for energy and health. And so nanoelectronics is a topic by itself that, you know, millions of people work on it, and energy is a big topic by itself, and health is a big topic by itself also. So you can't, so the reason I put these on, because kind of work that I do with my collaborators kind of touches upon all these different topics, but my main area is really nanoelectronics, or electronics in particular. So I just want to make sure that that's pretty clear. So this outline is kind of suggestive. I'll go through the objective and talk about some devices and some circuits and applications and prostheses and some of the work that we started with Clemens Burda in chemistry department about 8 years ago to look at nanophotovoltaics. I'll talk about that, and that would be applications in energy. And I have a little project to develop sensors, wireless sensors, to go inside engine and monitor the UV spectrum of light that is given off by the combustion process to optimize the efficiency. And then I'll conclude. So when you talk about sensors that you want to put in biological environment, small is really good. It can have some side effects, like, you know, if you put something that's nanometer scale and you don't know where it ends up after a person goes through the gym, or if the activity level goes up, you want to make sure that if it's a nano sensor, it's a robust nano sensor. So with that caveat, nano is good because most of the processes that happen inside the cell or across the cell, they go through these nanometer type of interfaces. So either it is through a membrane, which is about 5 nanometer bilipid membrane, or it is through nanopores, which is between 1 to 3 nanometers. So all the interfaces are basically nanoscale. And one of the good things that has happened during the past 15 years or so, it's this discovery that carbon nanotubes can be grown really, really easily and inexpensively. And since carbon is a good biocompatible material, it makes sense to look into applications of carbon nanotube-based sensors in biological environment for prosthesis and to design better electrodes. So we have done lots of work in this area, and I'll talk about some of them for you. So for those of you that may not know about carbon nanotubes, these are like graphite that are rolled back onto themselves. You can get them in single-wall or multi-walled versions, depending on how high temperature you use in growing them. They're really easy to grow. You need methane, which is basically a cooking gas, and a catalyst, something like nickel or iron, in order to grow them at 700, 800 degrees centigrade. They're extremely stable. All the carbons and carbon nanotubes are very happy to be there, and they don't have dangling bonds. Therefore, they don't oxidize easily unless you want them to. So at room temperature and in normal environment, they don't oxidize, and they're pretty stable. And you can adjust their electrical properties by putting oxygen or hydrogen near them. So that's really good as far as their applications in gas and chemical senses, but it's bad if you want to make devices using these carbon nanotubes that they have stable characteristics. So you have to passivate them if you don't want them to sense things in the environment. And they can also be added to integrated circuits, which is a great thing because integrated circuits have come a long way, and they're very sophisticated. You know, they're responsible for all these wonderful devices that we use, laptops and cell phones and stuff like that. But when you go to 45 nanometer node and beyond, so you want to look at things that are on the order of 10 nanometer or so, it becomes very expensive to make devices with 10 nanometer or 5 nanometer feature sizes. So by adding carbon nanotube inexpensively to an already made integrated circuit post-fabrication makes lots of sense. So most of the nanotechnology work that I'm interested in and I work on, I don't really want to eliminate anything. I just want to use whatever exists and make them better by adding these nanotechnology stuff. So key properties of carbon nanotubes are here. So the band gap so you can have semiconducting and metallic ones. Semiconducting ones, they have a kind of a semiconducting-like behavior. So they have a band gap that is kind of proportional to 1 over d, and E is the diameter of the carbon nanotube. And they can withstand large current densities. You can pass large current densities through them, and they don't deteriorate, which is a great thing. And you can now grow them. This is old. We can grow them up to 10 centimeter or so in a continuous manner. So they're hair-like structures. The aspect ratios are amazing. So you start with something that is, let's say, 1 nanometer or 50 nanometer diameter, and you grow them for up to 10 centimeter. Think about it in terms of aspect ratios. It's a highway that can run around the globe a bunch of times. That's the aspect ratio, right? So they're amazing stuff in that sense, and given that they are very stable and you don't need to do lithography to grow them, makes them really interesting. And they have pretty good thermal conductivity, and they can withstand large strains. So carbon nanotubes have been around for some time, 15 years or so. People have learned how to grow them easily. Most of the work that existed before we got into this were based on post-processing. So you would grow carbon nanotubes using one process, and then you add them to your structures in some fashion. And if you want to do this in a very controlled environment, you need kind of a nano manipulator, atomic force microscopy of some sort. And it takes lots of time, and the yield is very low. So there is no really added value per se for general purpose applications. What we started doing was to come up with a technique that you can grow carbon nanotubes between electrodes that you define using photolithography. So that way we try to make it more reproducible, less expensive, and come up with applications that readily require that kind of solutions. So the technique that we developed, Yan Ji, who graduated about a few months ago, and now he's in Georgia Tech, basically was one of the key people who developed this. So the idea is very simple. So you're going to bring in gas and stuff. These are the posts that I showed you. Let me see if I... Oh, looks like it doesn't want to go back. So these are the posts that I showed you. So what you do is on one wall you deposit carbon, and the other wall you may want to end up with iron. That's your catalyst. And the way you do this is by just tilting the sample over some kind of a heater that you put your iron pellet or your carbon source and evaporate. And you use these different walls to do shadow masking. That way you can end up with different materials on different part of the device. And you can do this across a wafer, so it is very scalable. And then the idea is that you kind of put this device with these different layers on different walls inside your reactor and bring in carbon-carrying gases. The carbon-carrying gases can be anything. It can be methane, which is the cooking gas. It can be acetone. We can put a little bit of acetone inside the reactor, and as you heat it up, it starts evaporating. That can be your carbon carrying gas. Actually, you don't need much, because just when we talk and stuff, there are all these hydrocarbons and CO2 and stuff that are generated by biological systems. That's enough to grow these carbon nanotubes. So you don't need much carbon in the environment to grow them. You can calculate the number of carbon atoms you need to grow one of these carbon nanotubes. So it is very small, right? So the distance between carbon atoms is on the order of 3.47 angstrom or so. And per unit length of this, you only need a handful of carbon atoms to grow it. So that's kind of interesting in that sense too. So you expose this to the carbon-carrying gas, and as it comes, it kind of carbon and hydrogen, they get dissociated, and carbon gets dissolved inside the iron, and it saturates it, and then the carbon ends up near the tip, and that kind of starts growing the carbon nanotube. This is pretty accurate model, by the way. People have done this inside transmission electron microscopes, and they have shown, there are videotapes out there. If you just Google, Google carbon nanotubes, you will see these videotapes, video clips, and it really grows very nicely. The interesting thing about growth is that you can't really dictate when it starts, but as soon as it starts, it goes very fast. So typically, what we do is we kind of set the temperature and the flow rates and stuff as indicated in there in order to start growing these things, and this is an example of what we end up with. This, we have done it in 10 minutes, but most of the action happens in a fraction of a second. But you have to put it in there and wait for things to start happening, and that we can't dictate. At least till now, we haven't been able to dictate. So the whole thing happens very quickly once it happens. The reason I can see these carbon nanotubes as very kind of charged up white lines in there is because they are charged up. The scanning electron microscopes don't have the resolution to show these things if they don't charge up. So electron beam comes, and then it charges these up, and whatever electron is there starts repelling the other electrons that are coming. So it kind of, therefore you can see them. They kind of look bigger, and because of that you can detect them. So once you grow these carbon nanotubes between these two posts, then the posts can provide you with electrodes readily, and you can go ahead and look at their IV characteristics, current versus voltage characteristics. And if you kind of put you can put variety of different materials on these walls and make some interesting switches and non-volatile memory devices, stuff like that we have done. This particular trace shows the sensitivity to hydrogen carrying gases, and you can get the same kind of traces for oxygen carrying gases. This is an example where copper sulfide is used for solid electrolytic memories for non-volatile memory devices. So if you put copper on the other wall and grow carbon nanotube onto the copper sulfide, the IV characteristics and stuff are very nonlinear, and they show on and off very nice separation between off state and on state. We are actually continuing this as part of our DARPA effort on nano-electromechanical switches. This is kind of a cluster approach to nano-electromechanical switches. So it's kind of ultimate nanomechanical switch. this kind of shows up front. So copper sulfide cannot be taken up to 700 degrees centigrade or so. So what we did was we grew carbon nanotube between these two walls. This wall was covered originally with copper, and then after we grew the carbon nanotubes, we took it out and sulfidized the copper. And if you look at some of the carbon nanotubes and stuff, they kind of start sagging, because when you take copper and convert to copper sulfide, the volume increases by a factor of 2. And because of that, the carbon nanotubes are not stretched anymore. They kind of start sagging. These are some of the IV characteristics and stuff. I really don't want to bore you guys with lots of these details and stuff, but the important thing is that you see this on and off behavior. And these are the world's smallest area devices that are not done using electron beam lithography or X-ray lithography or some fancy technique. You grow carbon nanotube onto a functional layer, and you get 3 nanometer squared area. Now try to do that with electron beam lithography, and I'll give you a couple of PhDs before you are done. So they're very challenging problems if you want to do this using electron beam lithography, right? So you guys that work with electron beam lithography, you know, 30 nanometer you can do, maybe 20 nanometer if you work really hard. You know, 3 nanometer square contact areas are unheard of. And you have to kind of stand on your head and kind of do a whole bunch of other stuff for it to happen. So it's pretty difficult. So multi-walled carbon nanotubes, they have some other interesting characteristics. If you kind of hang on to both sides of the carbon nanotube, these multi-walled ones, and kind of pull on them, they start telescoping out. And when they telescope out, these different carbon atoms on different layers, they grind against each other, kind of quantum mechanically. And as they do that, the resistance or conductance between these two posts basically change periodically, because these carbon atoms are arranged in periodic arrays. So you can use that as strain gauges with very large gauge factors. And you can use them, for example, to track position at nanometer scale. And there are lots of devices that people are working on. This careful study was done by my friend Andrew Zettel at Berkeley, who put these multi-walled carbon nanotubes in a TEM and attached 2 posts. In this particular case, one was AFM tip. By the way, we have a couple of these in my lab on the 7th floor in Glennon. If you guys are interested, you're welcome to contact Lucian, who is sitting in here, and we'll give you some demos regarding how they work and stuff. And this is a TEM image, so you can see he pulled it, and then they kind of became elongated, and as they kind of telescope out, the resistance changes. There's another theoretical work that was done by a Chinese group that showed that if you look at the conductance, this is a very careful study. The conductance basically goes up and down as these different layers are telescoping against each other. So this was kind of intriguing, but if you want to make a device with an AFM tip in there, I don't know about you guys, but that kind of worries me, because then you have to spend $150K on an atomic force microscope to make a strain gauge that you're going to sell for a couple of cents, right? So, so it was interesting to come up with, use our self-assembled, self-welded technique to come up with devices that we can readily make, and they are scalable and reproducible, all that. So the idea was to kind of use a cantilever beam and put these posts on a strategic location on the neck here. And so when you bend this gap opens up, and when it opens up, it enables these carbon nanotubes to telescope out or in, and then you can use the current versus voltage characteristics between those 2 posts to see what's happening. So this is kind of an SEM image of cantilever beam before it was released. This is the SEM image of the gap with carbon nanotubes in there that we grew using the technique that I mentioned. I hope you guys can see this. Oh. Can we turn off the light? Thank you. Yeah, the danger is that I know that even with lights, I'm going to put you to sleep. Without lights, for sure. And I won't even be able to see what I'm doing, right? So this is kind of a side view, so you can see the gap in there. This is the cantilever beam. That's where we grew the carbon nanotubes. This is another shot of the carbon nanotubes inside the gap. And this is current versus voltage between the posts that I showed you. Oh, gosh. How do I get out of this? So these posts are kind of come with this device for free, right? So we look at the IV between these two posts, and you can see that IV basically changes depending on the strain that you put on the system. So depending on how much you bend the cantilever beam, the IV has different slopes, which means that it has different resistances. So I can look at current versus the strain as it's shown in there, and you can see these modulations ups and down. These are due to carbon atoms in different layers of multi-volt carbon nanotube kind of grinding against each other. So they kind of go over each other, and then they're kind of in their troughs and so on and so forth. And there is a modulation as kind of, there is kind of an overall change too, which is explained by Andrews et al. It's kind of a 1 over R dependence of the effects that we see in the electromagnetic regime. You can also do dynamic measurements by kind of vibrating this and seeing and trying to detect the vibration spectrum of the cantilever beam by looking at the piezoresistive signal. So this enables you to come up with a piezoresistive sensor that's very small, can be readily grown inexpensively, and it doesn't have the problems of scaled piezoresistors in silicon. So if you want to take silicon piezoresistors and make them smaller and smaller, as the volume becomes smaller, the fluctuation in doping concentration, the statistical fluctuation makes them with characteristics that vary dramatically from one device to another device. But carbon nanotubes are all the same, more or less. So although they are very small, but because of their structure, there is not much statistical variations in their structure. So kind of carrying the same theme, we became interested in using these carbon nanotubes that you see in there for nano switches for electronics and sensors. And one of kind of my agenda was to use these as electrodes for prosthesis. So you can come up with brain-machine interfaces where you have carbon nanotubes attached to some electrodes, and carbon nanotubes go inside the cells through these nanopores very easily, and provide you with a mechanism to interact with cells without destroying them, since these are so small. And also they enable you to look at the signals generated by cells. So we kind of created these carbon nanotube-based switches and discovered that the capacitance between them is exceedingly small. That's good in some applications, but for switching applications it's not good, because you want the voltage for the switch to be compatible with CMOS. So that kind of sets you around 1 to 2 volts. The capacitances that you get between these two are so small that you need like 10, 15 volts to switch them. Once you apply 10, 15 volts across these carbon nanotubes, as soon as they switch, they burn. So not a very good switch. Therefore, we kind of backed up a little bit and went back to the drawing board and came up with these tuning fork devices for our switches for DARPA, which was looking for 1 gigahertz, 1 volt switches, right? Some of you guys in the audience are also working on similar devices. So actually, there are 2 groups at CASE that are working for DARPA on this. So it's kind of an interesting area because once you make these switches, then you can make computers using these switches, and those computers would be extremely resistant to harsh environment radiation. They can operate at very high temperatures, stuff like that. And they also have a 0 turn-on time. So as soon as you turn them on, everything is stored in these mechanical switches, and you have your computer. So DoD is interested in this kind of stuff. So again, I just want to show you some important results that we have obtained. I think we were the only one who could demonstrate 1 volt switching. Actually, we demonstrated 0.8 volt switching. They were looking for 1 volt switching. And the competitors are Michael Rukas at Caltech, Roger Howie at Stanford, and the whole group of people who work on these problems. And they have been working on this for the past 20 years or so. And I think Dr. Koh knows all of them personally. So we were really lucky to be able to do this. Now, 1 gigahertz, right? They asked for 1 gigahertz. We delivered 3 gigahertz. So it's kind of interesting. Again, we were lucky because you see, you have 1 nanometer, roughly 1 nanometer gap between these tuning forks in there. And tuning forks are kind of interesting devices. So when you have a switch that, based on a cantilever beam, usually the ground plane is fixed, and some kind of a cantilever beam, you apply a voltage and you try to actuate the switch. In a tuning fork, it's a similar thing, but the ground plane also moves. So you apply a voltage, instead of this moving only, the ground plane also moves towards the switch. So both sides move. That gives you 1.4, kind of factor of 1.4, square root 2 type of thing, advantage in terms of voltage. So it kind of lowers the voltage that you need to switch. It also gives you something else. Because these are 2 coupled cantilever beams, when you apply a voltage, both of them are moving, although their velocity is the same as before, but the effective velocity is doubled. So the frequency, right? So the frequency becomes higher. Because of that, we were designing these for, roughly 1 gigahertz, and we were surprised to see that they are switching at much higher frequencies. Another important thing is that when you have 1 nanometer gap, air molecules don't find very pleasant to end up there, right? Because their mean free path is about a micron in 1 atmosphere at room temperature, and it is so small a place that you're not going to get many of these air molecules in there. Eventually, they end up in there just because of the tail of the distribution in the energy and stuff, and oxidize these contacts and deteriorate the switch. But at least for a couple of days, everything is fine. I'm going to switch gear now. So what we learned from these switches and beams and stuff like that, we started looking at some other interesting applications with Dr. Garbrick and Dr. Hillel Cheel in biology department. There were some interesting coming up with electrodes that are compliant enough so that they don't tear biological tissues, but at the same time rigid enough so that they're not going to kind of move around on their own, right? And they also wanted something that is electrically impedance matched to extracellular recording of neuron firings. So we had the carbon nanotube stuff, and we knew how to fabricate these cantilever beams. These things are known, by the way, for a long time, for about 30, 40 years. And Case was one of the first places that started doing these microelectromechanical structures about 35, 40 years ago, if I'm not wrong. The structures themselves are not new, and electrodes, they're not new. They have been around for a long time. Actually, this area of doing prosthesis using electrodes has been around for about 100 years, more precisely since Volta's time. Volta, the guy who basically discovered batteries and stuff like that, or the battery effect, was one of the first guys who had kind of metallic electrodes accidentally or intentionally, I don't know, nobody knows, contacting frogs, and frogs started twitching and stuff, right, in the presence of some acidic solutions nearby, lemon juice and stuff like that. So everybody makes these electrodes and sticks it into something, right? So the question was how to make them so that they have the desired mechanical and electrical properties. So this kind of shows buccal ganglion and C-slug. C-slug is a good kind of control example or biological system. Hillel Cheel is a world expert in these animals, and he has kind of usually 20 or 30 of them in his lab. And he's interested in collaborating and coming up with new ways of doing transduction. So these cantilever beams, they have mechanical impedance comparable to what you get in biological systems. And their electrical impedance, these patches that you see, these platinum patches that are our electrodes, when they're glassy, when you don't add carbon nanotubes to them, their electrical impedance is pretty high. So by adding carbon nanotubes to these, we managed to make them really good. So you want those electrodes to be very small, so you can record, you can have a large density of recording, right? You want to, in buccal ganglion, in that particular buccal ganglion that we're looking at, there are about 3,000 neurons. The largest neuron is anywhere between 50 to 100 micron. And till now, at best, 4 neurons are mapped. And Hillel is interested in looking at the neural circuitry. So he wants to know if the sea slug feels hungry, which are the neurons that start firing, and if he decides that it's enough, I have eaten enough, then which neurons start inhibiting firing and inhibiting the process, and that kind of stuff. So in order to be able to do that, you need to be able to record from neurons that are on the order of 10 micron, 5 micron, and deeper inside the buccal ganglion. You have to be able to look at 3,000 of them. So now we have 4. To go from 4 to 3,000, you need to have very, very small electrodes. When you make electrodes very small, then they don't see the neuron firings because their resistance becomes so large. So you need to add some kind of nanotechnology to it to increase their surface area. So while they are very small, they can look at these and detect these neuron firings. So by adding these hairy-like layers, whenever I don't want it, it works. Should I just do this? Previous, yeah. I think I got it working. For some reason, it doesn't want to go back. Oh, OK. So these electrodes, we have a whole bunch of them now, and they are kind of seeing about 500 of those neurons. And we added these hairy layers on them. These are carbon nanotubes grown in a very simple low-pressure chemical vapor deposition system. You can see we can cover them uniformly with these carbon nanotubes, and they increase the surface area tremendously. So here is the objective for the sea slug project, by the way. So what we want eventually to do with Dr. Garbrick and other collaborators is to embed these electrode arrays with wireless telemetry and maybe energy scavenging capabilities into the sea slug, and do the following thing. When the sea slug decides that he or she is hungry, we want to push a button externally and convince the sea slug that no, he or she is not hungry, well fed, and wants to do something else. And do the opposite. So if we can do that, then we feel that we will fully understand, we have fully understood the neural circuitry in the brain. By the way, there are many other interesting applications, like Steve Garbrick is our associate chair. So if you want your grade to be approved, if you have one of these devices, then you can find some applications there, right? So you can do kind of remote control of people, right, eventually. But that's just a joke. Don't take it too seriously. I don't think that Dr. Garbrick will let you do that. And this is Dr. Garbrick's circuit there that enables you to do bidirectional telemetry, I believe, right? This is my collaborators are Steve and Hill on this. And the idea is to be able to both read and actuate these neurons. I'm going to, again, switch gear a little bit and kind of talk to you about telemetry stuff from my point of view, right? So I'm kind of analog device, circuit device, nanotechnology person. So I like to keep things, circuits and stuff, very simple. So talking about wireless telemetry, there was this opportunity to come up with harsh environment sensors that can detect UV light inside the engine. So we came up with these kind of oscillators with silicon carbide devices that are pretty well suited for harsh environment because they have a band gap of about 3 eV, and they are very, very rough materials. Silicon carbide is used in abrasive cloths and stuff for grinding. They have lots of industrial applications for this. Now, this silicon carbide is not the same kind of stuff that you find in abrasive materials. It is single crystal, and it's pretty expensive. It's about $14,000 for 2-inch wafers from Cree. But nonetheless, we kind of have made these integrated circuits and stuff using silicon carbide, and discovered that you can have kind of a UV-sensitive optical field effect transistors, and this shows the UV sensitivity of these FET transistors and their response to different type of UVs in there. So I thought that I mentioned this to you, and then we looked at the power consumption and discovered that it is not that good. So the next thing to do was to kind of use a tunnel diode. Tunnel diodes are kind of interesting devices. They have very nonlinear IV characteristics, and they switch on and off. And the idea is that if you put it in an LC circuit, just at the right moment, if they switch on and off, they will kick in a certain amount of energy into the circuit and keep it oscillating. So in that sense, you can kind of sustain the oscillations. These are exceedingly low power transmitters. Vin is about 0.28 volts, and the current for this particular device was 0.3 milliamps. So you can embed these in one of those wireless telemetry devices, and it can go a very long time on a lithium ion battery. Of course, you have to down convert it from 3 volts, but it is, they're a really nice device, and this is the output spectrum as a function of the voltage that you apply there. They work really well. Now, if you want to do this in silicon carbide, it's a major effort, and that's one of the things that we have started working on. But once we do it, then we are going to be able to come up with very low power wireless systems on silicon carbide for engine diagnostics. I'm going to shift gear a little about it again and talk about energy, right? So energy is in everything, right? So if you have a wireless telemetry that uses very small amount of power, you can potentially save lots of money by putting them inside the engine and using them to improve the efficiency of the combustion engines. If you can improve it by a fraction of a percent, that would translate to billions of dollars, right? Because if you multiply all these jet engines and combustion engines that are at work, it would save lots of money. This is kind of more directly related to energy scavenging from sun. You know, have to come up with solar cells that are inexpensive, and you can do it in a variety of different places. It is kind of interesting, since we are alive, right? We have to have sun, and that is the case in most places on Earth. So sun is very plenty, and therefore, if you can come up with a mechanism to convert it to electricity, it makes lots of sense. You can use it almost everywhere. Now, to just show you where we are, this is watts per meter square, right? So, for example, I think we are right there, and that's kind of greenish. That's about 160 watts per meter square. So if I put 1 meter square solar cell with good efficiency, this kind of assumes very good efficiency, 30% or so, then I can get about 160, 170 watts of power out of that solar cell in Cleveland. And if you look at this band, it's pretty wide, right? To compare this to biofuel, biofuel is 0.04 watts per meter square. So it is very, very small compared to what you can get out of sun. So it makes lots of sense to go solar cell. So one of my students, who I think is back to Thailand, made this. Fuel is bad, right? Because it's expensive, lots of politics involved with it. It's bad for the environment. Biofuel is also not that good because it is very inefficient. 0.04 watts per meter square of all these cornfields and stuff. You know, you have to convert lots of corn to be able to make up for a little bit of this. And you know, solar energy is for free. So there are many hands in this game, right? There's Bob Green at Australia, who is kind of world authority in solar cells, and there are a whole bunch of people who are working on solar cells and stuff. It has been around for a long time. NASA Lewis Research Center, which is kind of granddaddy of NASA that we have right now, was one of the pioneers of improving the solar cells for space applications, and lots of colleagues at CASE, they have worked on this problem for a long time. What is new in the solar cell field is, again, using these nanotechnology stuff in order to make them inexpensive, more efficient, and out of materials that are readily available, right? So that's the idea. So titanium oxide, which is used in powders and paints and all that, dirt cheap nanotechnology material that's available. And people have started looking at using titanium oxide, which are produced by tons, even in Cleveland, right, to make these solar cells. The way it works is kind of interesting. There are two types of solar cells, p-n junction based and these type 2 nanoparticle based. The p-n junction based, you basically have a built-in electric field inside the device. You shine light, You generate electron-hole pairs, and the built-in electric field separates them and produces a current out in the external circuit. Now, for that, you need high crystallinity. You need very small amount of defects inside the material, so it makes it expensive, right? There are some materials that are better in their polycrystalline form. One of them is copper indium diselenide. But copper indium diselenide has selenide in it, has indium in it, there's cadmium in it, it's bad stuff, right? So although you can kind of make it in polycrystalline form, but it's not very desirable environmentally. Titanium dioxide, on the other hand, is in everything. So it is good to look at these type 2 solar cells. Type 2 solar cells work based on a different principle. So you can think of these p-n junctions kind of distributed among individual particles, nanoparticles. Then you have to come up with a way to harvest all that energy in different forms. So we started looking at this problem, and it made sense to not have only one type of energy conversion device based on these nanoparticles, but have 3 layers. So the top layer would basically get the photons converted to electricity. The second layer, probably you want to have some kind of a thermophotovoltaic devices, maybe thermoelectric type of approach. And the third layer to have a Stirling engine in order to be able to get most of the energy out of the sun. I'm not going to go through the details of all these different parts of the solar cell that we have, but this is just for those of you guys who are interested. You can see these and then see me at the end, and I'll give you references on this. And the last layer, we want to put in a Stirling engine. Stirling engine is really an interesting, very high efficiency engine, and you can make them in very thin layers. And once you do that, then this stack of 3 different layers, each layer is inexpensive, and they can be basically molded onto each other, can provide you with a wide coverage of the most spectrum of, most of the energy in the sun's spectrum. So in order to be able to do this very efficiently, you need to be able to come up with methodologies like plant leaf to intergrow different parts of the solar cell into each other. For that, you need a technique to grow fractal geometry structures, right? So the idea would be, this would be, let's say, titanium dioxide, and then I would have an electrode that would grow tree-like structure like this into this, and then these 2 electrodes on both ends would act as my power collection electrodes. So what we have that works for us is the ability to go to individual nanoparticles and look at their characteristics. So to just give you an idea of what this means, this is 50 micron by 50 micron plate. In 50 micron by 50 micron plate, you can have few zillions of, let's say, 1 nanometer diameter nanoparticle. Each of these nanoparticles, by their nature, these are not carbon nanotubes, so they're going to have lots of variations between their characteristics. So we need to know the winners. We need to know which nanoparticles are good at this kind of conversion of photons to electricity, and which nanoparticles are not good. So in one shot, we can do many, many experiments in parallel. All we need to do is to have the right tool that we have, that's conducting AFM stuff that we have set up in our lab on the 7th floor in Glennon, go to different nanoparticles and look at their characteristics under illumination. And the nanoparticles that are the winners, we can number them. Number 15 is better than number 17. And then we can take these to the SEM lab that we have on the 1st floor, look at their characteristics very carefully, and reproduce those. So leave behind everything else, only stick with number 15. And if we can keep doing this, it's kind of a genetic algorithm approach for improving the properties of our nanoparticle solar cells. So we can get rid of all the weak links, right? So if we get rid of all the weak links, the strong guys are going to be there. It kind of sounds bad, because diversity is always good, right? So for the diversity, what we can do is to look at their spectral response. And spectral response of number 15 may be good around 2 eV. Number 17, which is bad around 2 eV, may be good at 1 eV. We can also do that. So we can kind of, in a very engineering manner, we can select number 17 for 2 eV, number 15 for 1 eV, and the rest of them to cover the whole spectrum, you see. So that's what we are doing. So in order to show you that it's not all talk and there's some action, right? I would like to show you how to grow these fractal geometry stuff. This is in very slow motion, right? So at each pulse, I am assembling these nanoparticles that are inside the solution onto this tree. And I can reverse the polarity, and I can grow it from the other side. You're going to see it in a second, OK? So now, it's not as good as it looks, actually, because these structures are not very stable. So one of the research that we are doing is to come up with a way we can grow them bushy, we can grow them lean, we can grow them mean, we can grow them any way that you want by choosing the voltage and the frequency and the concentration of the nanoparticles inside the solution. Now, I'm not going to bore you guys anymore than I have to, right? It's always a pleasure to give one of these talks. You see, I'll threaten you with something. And that is, if you don't ask questions, I have few more presentations with me. So let me just fire up and see if there are any questions. So actually, I want to go to something else very quickly, and then I'll let you guys go. You know, I decided instead of giving you lots of formula and equations and numbers and stuff that I'm sure you get plenty of it in Dr. Garbrick's class, to give you something exciting, right? So we have been working on these. So one of the very controlled ways of growing these carbon nanotubes and variety of different materials is using something called tip-based nanomanufacturing. And how can I turn this off? Yeah, if you can turn it off, if it can be turned off. This is kind of first in the world, actually, I think. So we are coming up with these very, very fine nozzles and probes to generate these plasmas to deposit in a very controlled manner nanoparticles or etch them and stuff like that. This is very preliminary work. I just want to show you the kind of scope of things that we are working on. This is also supported by DARPA, as you can see there. And we are getting some very interesting results. I think a bunch of people in the audience are involved in this project. So the idea is to bring in, let's say, methane through this nozzle and use this plasma to grow carbon nanotube exactly where you want and make it scalable. So these are two different types of plasmas. They're based on helium. One is positive and the other one is negative. And you can do different things with them. Before I let you guys go, since I have like, what, 10 more minutes? There may be questions. Well, I'm trying to avoid questions, maybe. Well, well, OK. So maybe we can start the question and answer process. And I have one more thing to show, which I think you guys will like. Actually, I'm trying to solicit people who may be interested in that. I know that one person is interested, but let me just put that up. So if anybody wants to ask questions, hopefully I'll be able to answer. Yeah, I mean, while you guys are asking, maybe I'll explain this quickly and then we can move on. There is an interest in, again, from the energy point of view, there's an interest to come up with micromotors that are very efficient, and you can use them in a variety of applications to steer microphones in different directions instead of, or using microfluidics for pumping. Actually, there is a pumping BAA coming out, so you guys may be interested in to put these micro pumps on chips, right, for so that you can put these analytical tools on chips, so you can do mass spectroscopy or look at pollen count inside the air or some allergens that you may be interested in inside the air. And you can use these in order to push things or pull things. This is a very efficient micromotor that we have fabricated a few years ago, and it is based on rectification of oscillatory motion. This guy is moving back and forth, and using this micromotor and the fins that we have arranged, we kind of convert this oscillatory motion into rotation. I have a linear version of this. I don't have the video. I think it's at the end. I don't want to bore you guys with. It's kind of a fishbone type of thing. When they move, they start kind of moving forward, and you can kind of reverse the phase and stuff and pull it back. So these are some of the stuff that we are working on. We are very busy and lots of excitements in the lab and always looking to hire new people. And actually, I still have like 2 more positions open. So if anybody's interested, please see me or Lucian here, and we'll try to get you into the lab and see what you're interested in. Thank you.
All right, let's start. Okay, we're now ready for questions. I'm going to ask the first one then.
Uh-oh, I'm in trouble.
Going back to the carbon nanotubes. One of your early slides showed that carbon nanotubes have a band gap voltage, and it goes as the reciprocal of the
diameter. So smaller they are, the semiconducting version of them, they become higher band gap. It usually kind of saturates around 1.2, 1.3 eV. So in the limit of making them 0, the band gap becoming infinity, it's not really physical. It doesn't have a physical meaning. So bigger they are.
So these nanotubes are not simply conductors.
Yeah. When you grow carbon nanotubes, you get 3 kinds. They're called left-handed, right-handed, and neutral. The left-handed and right-handed ones, they are semiconducting, and the neutral ones are metallic. So you can think of these as kind of sheets, graphene sheets or graphite sheets that you kind of fold back onto them. When you're folding, you can either advance it or retard it or come exactly where you kind of, similar points come onto themselves. So this gives you kind of the neutral one or the armchair one. And the other 2 chiralities, the kind of advancing and retarding, give you these 3 different type of carbon nanotubes. They give you 3 different type of conductivities. So semiconducting part kind of type versus metallic part. But even metallic ones are resistive. It's only the sign of the change of their resistance as a function of temperature that kind of determines whether they're metallic or semiconducting. So in the case of semiconducting ones, when you heat them up, the resistance goes down. In the case of metallic ones, when you heat them up, the resistance basically goes down. In the case of semiconducting one, the resistance goes down, and in the case of metallic ones, it goes up. So
since they are semiconductors, does anyone make transistors out of these?
Yeah. There's a large community that has worked on these, and there are some very interesting results. The problem has always been to grow the right chirality exactly where you want them to be with the right property. So these 3 things are pretty challenging. Most of the work that has been done by Charlie Lieber at Harvard and Fidian at IBM, they use AFM in order to pick the right kind and put them between the right electrodes. So they spend like a couple of days, lots of dedications in order to get 1 transistor and report and publish 1 paper. It's very high quality stuff, but
I wish I could do 1 paper per transistor.
Right.
All right. Other questions? All right. Well, you know where to find them if you come up with something later on. Thank you for attending.
I have 5 more minutes. If you don't ask questions, I have a few more presentations. So I'm just kidding. But thank you very much for attending this talk. I really appreciate your participation. Thank you. Hello, Meryl. Thank you very much for coming. Thank you.